All right, here we are talking about projectile motion. This is just an extension of linear motion, but we have motion in two linear directions, essentially. So it's objects that are shot in the air, thrown in the air, kicked in the air, things that fall off cliffs or other fun things like that. And so there's a few things we're going to go through. All right, constant velocity in the x direction. So the only thing that slows an object down when it's moving side to side is wind resistance. So to simplify this for our purposes, we ignore wind resistance, and if that's the case, then the horizontal velocity never changes in the x direction. All right, so that's a real important aspect of this whole thing. So we have constant horizontal velocity. All right. In the vertical direction, we have the acceleration of gravity because all of these things are falling. All right, all of these things are falling. So we represent acceleration of gravity with g, and it's pointed in the downward direction. For convention, to make it simpler, and you can pick this, but I will always say that up is the positive direction, and we need to specify that on any picture or diagram, so I will do that as you see here. So the acceleration of gravity is also constant, and that is in the vertical direction. So we have constant horizontal velocity, and we have constant vertical acceleration. All right, so trajectory, path traveled by a projectile, so that can look a few different ways. So if we're on flat ground, of course, we have, something like that. If it's launched at a higher angle, of course, it's going to go higher. It may or may not go the same distance. And then we can also have things like this, right, where we have maybe there's a ball that rolls off a table and it falls. Or when we get to projectiles at angles that may be launched or kicked, and it has a higher trajectory, not a horizontal trajectory. So we'll look at both types, starting and ending on the same height, or starting and ending at different heights. All right, so here's what we do. In order to get through these problems, there's a couple things. We have to split the motion into horizontal motion and vertical motion, and that is the most important part. All right, we're going to make a little chart. I'll show you what it looks like in the example down here. The horizontal motion is the same of an object moving at constant velocity. So the side-to-side motion, side-to-side velocity never changes. The vertical motion is exactly that of something in free fall, whether the object is moving up, like here in this first half, right? It's moving up but slowing down, and that's because of the acceleration of gravity, which is pointing down. And then when it starts coming back down, it's moving down and it's speeding up all the way down, right? And again, because of the acceleration of gravity, always pointing us downwards. The horizontal motion and the vertical motion are connected by time. So if you think about it, we split up the motions as if it is two individual types of motion, but they're happening together. And that's pretty obvious, I guess, but the connection between the two motions is time. They are both in the air for the same amount of time, moving side to side and moving up and down. All right. So the time it takes to hit the ground is the same vertically and horizontally. So that's going to help us. All right. So let's do an example here. So first thing we do is draw a picture. So we have a stone thrown horizontally at a speed of 5 meters per second from a height of 78.4 meters. And the time it's in the air, I'll find the time it's in the air and the horizontal distance from the cliff. All right, so let's go ahead and start this. So like I said, you start with a picture. So we have our cliff. All right, here's our somebody throwing the cliff. or throwing the stone off the cliff, and it's going to fall. And it's starting totally horizontally, all right? And then we have our height. I guess it says the cliff is 78.4, but we're going to go the height that it's thrown from is 78.4 meters. Okay, we want to find the time it's in the air and the horizontal distance, which is this, delta x. That's how far it ends up away from the edge of the cliff. And we also want the x and y components of the final velocity. So that will tie in some angle parts to us here. This isn't going to hit the ground moving straight down. It's going to have a slight angle. Okay, so I'm going to draw this velocity vector first. The original initial velocity vector, I'll do this in red, is pointed totally horizontal and to the right in this case, 5.0 meters per second. So that's our velocity vector, and that helps us here. So we have two types of motion. We have horizontal and we have vertical. All right, and then we have our kinematic variables. We've used these many times for linear problems, and we're going to use them in the exact same way. Just now we have two different sets of linear data, essentially. All right, so we have a horizontal speed of 5 meters per second. So that is our initial, and it is our final horizontal velocity. Okay, and then if watching the vector video, any horizontal vector that is totally horizontal has a vertical component of 0. Okay, and so if that's the case, the initial horizontal velocity is the entire magnitude of the vector, and the vertical component of the initial velocity is 0 for a horizontal projectile. There is no vertical motion right at the beginning. Of course, gravity takes over and it starts pulling it down, so it gains vertical velocity. So final velocity is not 0 the moment before it hits the ground, but it's going to be some negative value because, oh, and I forgot to put this, we have to do our coordinate system. I'm going to say up is positive. So that means the downward direction is negative. So at the final, it's going to have a negative final velocity because it's moving downwards. It's going to have a negative displacement, and it's going to have a negative acceleration because of my coordinate system. If you want to make down positive, then you would have a positive final velocity, a positive displacement, and a positive acceleration. It is your choice, but I think it's a little easier just to make up positive, down negative all the time. All right, so this is the distance that the rock falls. So that is the vertical displacement. And then we know that the acceleration of gravity is a constant value. I'm going to use 10 meters per second squared. So it's negative 10 meters per second squared. And then over here, if you do not change your velocity, then you have an acceleration of 0. Or you could look at it here. The acceleration vector is pointed down, and therefore it has no horizontal component. So there is no horizontal acceleration as long as this is totally pointed in on one of the axes. Okay. All right, so for kinematics, you need 3 to solve, but you will run into problems on this side if you try to start over here. With these two numbers being the same and this being 0, makes it tough. So we want to start over here, and then, as we mentioned, we'll solve for time, and then these are going to be the same. Okay. All right, so here we go. Now what we have to do, we're solving on the vertical side, and we're going to solve for time. So let's try this. Delta y equals vi times t plus 1/2 at squared. All right, nice part about this, initial velocity is 0, so that whole thing goes away, and then we solve for t. So what we end up with is t equals 2 times delta y divided by a. And it's t squared, so we take the square root. Fill that in, 2 times negative 78.4 meters divided by negative 10 meters per second squared. And so when we do that math, we get an answer of 3.96, which I would round to 4.0 seconds. So there's how long it takes for the rock to hit the ground. And we place that over on both of these. All right, now over here we have enough to solve for delta x. All right, so we'll do that. Let's see, whoops. Okay, so we can use the same equation that we just used. So we're going to use delta x equals vi times t plus 1/2 at squared. Now, acceleration is 0, so that goes away, and you're left with this very simple equation. We want to find delta x. So we have initial velocity 5 meters per second times the time of 4 seconds. So we have a horizontal distance of 20 meters. All right. And I'm going to just leave it there. For right now, I'm not going to worry about the components of the final velocity. If you want to work through or you have questions on that, please let me know. So here's the other problem. I'm going to let you kind of work through this. You accidentally throw your keys horizontally at 8 meters per second from a height of 64 meters. Find the range. So that's looking for delta x. All right, that's what you're solving for. Set it up the same way. Establish your coordinate system. And let me know if you have any questions.